Wind is the next of the major factors affecting the range of an aeroplane. Headwinds will cause the aircraft to travel slower over the ground and therefore cover less distance for a given level of fuel consumption. Thus, in headwinds, range is reduced. In order to minimize this effect, the speed of the airplane is increased by a margin slightly less than the amount of the headwind. The increase in speed will increase the thrust and the power required, and therefore the fuel consumption. But on a positive side, the aeroplane will be exposed to the headwind for a shorter time period if it is flying faster. This higher speed then recovers some of the range lost caused by the headwind. On the contrary, a tailwind will increase the ground speed and increase the distance covered for a given level of fuel consumption, thereby increasing range. For maximum range with a tailwind, the speed for the best range should be decreased slightly so as to reduce the thrust and power required. This will therefore reduce the fuel flow and increase the range a little more. The reduction in speed is slightly less than the speed of the tailwind component being experienced. The headwind and tailwind speed changes can be seen on the drag and power curves for the jet and propeller aeroplane. However, to simplify the graphics, we'll just concentrate on the drag curve for the jet aeroplane. With a 20 knot headwind, the origin of the tangent line moves 20 knots to the right. Notice that the tangent meets the curve at a point corresponding to a higher speed, thus confirming that in a headwind, the speed for best range is higher. The opposite is the case in a tailwind scenario. With a tailwind of 20 knots, the origin of the tangent line moves 20 knots left. Notice that the tangent meets the curve at a point corresponding to a lower speed. This confirms that in a tailwind, the speed for best range is lower than in conditions of zero wind. The effect of altitude on the range of an aeroplane is important, especially for a jet aeroplane. On screen is the formula for the specific air range for a jet aeroplane. Let us examine how the variables change with increasing altitude. As aeroplane operating altitude increases, the colder air and requirement for increasing RPM cause the specific fuel consumption to decrease, which will help to increase the specific air range. However, there are two other variables left to consider, namely the true airspeed and the drag. If you think back to the part of the lesson where we were analysing the effects of altitude on the various speeds, you will recall that if the aeroplane operates at higher and higher altitudes at the constant indicated or calibrated airspeed of 1.32 VMD, the true airspeed increases. The effect of increasing altitude and therefore increasing true airspeed acts together with the reducing specific fuel consumption to help increase the specific range. However, you will recall that with altitude, as the true airspeed increases and the local speed of sound decreases, the Mach number increases. This means the aeroplane is approaching the speed of sound and approaching the maximum operating Mach number, MMO. The problem with this is that beyond a certain Mach number, the compressibility factor and approaching shock wave will cause drag to increase. This will be detrimental to the specific range. On the graph, you can see that the range stops increasing with altitude because of this effect. Consequently, there will be an altitude beyond which the range starts to decrease. This is because the Mach number will be too high, and the penalty due to drag will outweigh the benefits of increasing TAS and reducing specific fuel consumption. Consequently, the specific air range will start to reduce. You will notice on the graph that there is an altitude at which the specific range is greatest. In our example, this is 33,000 feet. This altitude is called the optimum altitude. It is defined as being the pressure altitude which provides the greatest specific range, or fuel mileage, at a given weight and speed. Flying higher or lower than the optimum altitude will decrease the range of the aeroplane. It is important to understand that the optimum altitude is not fixed. You will recall that as the weight decreases through fuel burn, the drag curve moves down and left. Therefore, the best range speed, 1.32 VMD, falls and the total drag decreases. Therefore, with decreasing weight, the aeroplane needs to slow down to maintain the best range speed. As it does so, the Mach number will of course also decrease, meaning that the aeroplane is not limited by the high Mach number and corresponding high drag. This fact allows the aeroplane to climb a little. As the aeroplane climbs, the Mach number will increase again to its previous limiting value, and drag will increase back to its previous value. But more importantly, the higher altitude has increased the true airspeed and decreased the specific fuel consumption. Therefore, the specific air range increases. This means that over time, as the weight decreases with fuel burn, the optimum altitude increases.